Dark holes are among the most captivating and puzzling phenomena in the universe. They are incredibly powerful, yet at the same time, they remain largely invisible to us. A black hole weighing 2 to 4 times the mass of the Sun can exert such a strong gravitational pull that nothing, not even light, can escape. Despite their elusive nature, recent advancements in our understanding of black holes have provided groundbreaking insights, bringing us closer to uncovering the mysteries of these cosmic giants. The journey of studying black holes has been long and gradual. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. However, at that time the concept was purely theoretical, and it took several decades for scientists to find concrete evidence. In the 1960s, astronomers studying the Cygnus constellation discovered an incredibly bright blue star emitting X-rays. This star was not a dead object, but instead it was orbiting a massive unseen object. Upon further investigation, they realized the X-rays were being pulled into this mysterious object, later identified as a black hole. This was a pivotal discovery, providing the first solid evidence that black holes were not just a figment of Einstein's imagination. The black hole in question, known as Cygnus X1, is located around 6,000 light-years from Earth. It is incredibly luminous, about 20 times brighter than the Sun, and extremely dense, generating a gravitational pull so strong that even light cannot escape from it. This was a significant moment in the study of black holes, as it not only confirmed their existence but also highlighted the need for further research into these enigmatic cosmic objects. Despite this discovery, the study of black holes was far from over. Astronomers soon realized that there could be as many as 100 million black holes in the Milky Way alone. However, detecting them is exceedingly difficult due to their invisibility and the complex nature of their gravitational influence. The Milky Way's black holes remain a subject of intense study, with estimates suggesting that there are potentially millions of them within our galaxy. The primary concern with black holes is, of course, their gravity. Their gravitational pull is so intense that anything that ventures too close is sucked in and compressed into a singularity. This process is known as spaghettification, where objects are stretched out and thinned as they approach the event horizon, the point of no return. However, it's not just theory. Scientists have speculated about what would happen to an individual falling into a black hole. The individual would be stretched gradually as they approached the singularity, eventually being reduced to a singular point of infinite density. Fortunately, this would happen so slowly that the person would not survive the process, and the last moments would be catastrophic. While the closest known black hole to Earth is located about 500 to 1,000 light-years away, this distance is still relatively close in astronomical terms. As such, researchers continue to study black holes closely, exploring their nature and the potential risks they may pose. In 2021, scientists succeeded in capturing the first clear image of a black hole, specifically the M87 black hole. This remarkable achievement was the result of several nights of observation, with scientists compiling images to form a comprehensive picture. This study revealed that black holes are not just endless voids but rather complex, multi-layered objects. Researchers discovered that a black hole consists of 3 distinct layers. The first layer is the event horizon, the boundary beyond which nothing can escape the gravitational pull of the black hole. Once an object crosses this threshold, it is inevitably pulled inward. The second layer is the photon sphere, where light can circle the black hole but cannot escape. Any light that enters this region is trapped, unable to break free from the black hole's immense gravity. Finally, the third layer is the singularity, the point at the center of the black hole where all matter is compressed into an infinitely small space. The fascinating aspect of black holes is that no two are exactly alike. While they generally share this 3-layer structure, the way each black hole functions can vary significantly. This variability poses challenges for scientists trying to study them. Researchers are forced to examine black holes indirectly by observing the radiation they emit and the surrounding gas and dust. Sending a probe into a black hole is impossible because once it crosses the event horizon, it would be crushed into nothingness at the singularity. Therefore, scientists have no choice but to rely on indirect methods to gather data. Despite the challenges, scientists have developed various hypotheses to explain the formation of black holes. One of the most compelling ideas is that black holes form when massive stars collapse under their own gravity after exhausting their nuclear fuel. In these cases, the star no longer has enough energy to counteract the force of gravity, causing it to collapse into a singularity. This concept of black hole formation from collapsing stars is a key area of study, but there is still much to learn. Each new discovery about black holes adds another layer of complexity to our understanding of the universe. Whether through new observational techniques or more advanced theoretical models, researchers are continuously unraveling the mysteries of these cosmic giants. As we continue to probe the depths of sufficiently massive, the secrets of black holes may one day provide answers to some of the most profound questions about the nature of the universe itself. This can continue until it forms a singularity, a point where the laws of physics break down. In studying the nature of black holes, NASA researchers focused on the heart of the M87 galaxy. Astronomers observed a massive whirlpool of superheated hydrogen gas spinning at an astonishing speed of 1.2 million miles per hour. The immense force of the gas disk should have caused it to fly apart, but it didn't. Scientists deduced that a massive object weighing as much as 2 to 3 billion suns must be at the center of the galaxy, preventing the gas from disintegrating. This object could only be a black hole. However, this isn't the only theory about black hole rotation. In 1963, New Zealand mathematician Roy Kerr used Einstein's theory of gravity to describe a rotating black hole. Kerr demonstrated that instead of collapsing into a point, a rotating black hole would form a ring or thin disk. This disk would rotate so rapidly that the outward forces would prevent it from collapsing. This rotating ring of matter is known as the ergosphere, the region around a black hole where the laws of physics start to break down. One of Kerr's most intriguing predictions was the existence of an Einstein-Rosen bridge, or wormhole. A wormhole is a theoretical passage through spacetime that could connect two distant regions of the universe or even two parallel universes. If you were to fall into a black hole instead of being crushed, you could theoretically be sucked through this passage and emerge from a white hole in a different part of the universe or another universe entirely. To understand how this works, we need to look at spacetime in Einstein's theory. Objects with mass bend the fabric of spacetime, creating gravitational fields that cause other objects to move toward them. Imagine spacetime as a flat piece of paper. If you place 2 points on it and draw a line between them, it shows how objects move through spacetime. But imagine if you could fold the paper, creating a shortcut between the 2 points. This is the basic idea behind a wormhole, essentially a shortcut through spacetime that connects two distant places instantly. Though wormholes are a staple of science fiction, they are also a predicted outcome of general relativity. No one has ever observed a wormhole directly, and the reason is that they are inherently unstable and would collapse quickly. However, if an Einstein-Rosen bridge exists, it suggests that black holes are not just cosmic vacuum cleaners but could be gateways to other parts of spacetime. Could we use a wormhole to travel through space and time? Unfortunately, the answer is likely no, at least not yet. Even if we could stabilize a wormhole, it's improbable that we could use it to travel faster than light. Einstein's theory of special relativity dictates that the speed of light is the ultimate limit for how fast anything can move through spacetime. That said, the idea of wormholes and black holes as potential pathways to distant parts of the universe, or even different times, has captivated physicists for decades. The concept that there might be shortcuts through spacetime, allowing travel over vast distances or even into the past, is a thrilling possibility. One of the most intriguing theories in this field is the Kerr wormhole, named after Roy Kerr, who first described it using Einstein's equations. A Kerr wormhole is a theoretical tunnel through spacetime that could connect two distant points, possibly two separate universes or different times within the same universe. The Kerr wormhole is often visualized as a ring-shaped opening, similar to the mirror in Alice in Wonderland, where walking through it transports Alice to a world where creatures speak in riddles and logic doesn't always apply. Similarly, passing through a Kerr wormhole might transport a traveler to another universe or a different time, where the laws of physics might be radically different from what we know. While the idea of wormholes as a means of interstellar or time travel is fascinating, it is also a topic of debate among physicists. Some argue that wormholes, particularly Kerr wormholes, might be unstable or difficult to traverse due to intense radiation and subatomic forces around their entrances. Critics also point out that Einstein's theory of gravity, which is used to describe black holes and wormholes, only accounts for gravity and doesn't include quantum forces, which govern radiation and subatomic particles. To fully understand these phenomena, a new theory is needed that combines the laws of gravity with quantum mechanics. This is often referred to as a theory of everything. Theoretical physicist Michio Kaku has been working on a theory of everything for many years. While there are many variations of what this theory might entail, the one that shows the most promise is superstring theory. Superstring theory combines gravity with the quantum theory of radiation. It suggests that subatomic particles are actually tiny vibrating strings, and the universe can be thought of as an orchestra of strings. Just as different musical notes correspond to different vibrations of a violin string, different particles correspond to different vibrations of a superstring. One of the fascinating aspects of superstring theory is that, as these strings move through time, they warp the fabric of spacetime, creating black holes, wormholes, and other interesting phenomena described by Einstein's equations. This implies that superstring theory not only unifies gravity with quantum theory but also explains many of the strange phenomena observed in the universe. However, there's a catch. Superstring theory requires 10 dimensions of spacetime for the strings to vibrate. This is very different from the 4 dimensions, 3 of space and 1 of time, that we experience in our everyday lives. It's hard to imagine what these additional dimensions might be like, but physicists have developed theoretical models to help us understand. One analogy is to think of a 2-dimensional lake inhabited by fish that are only aware of length and width. To them, there is no concept of height, and they can't imagine what it would be like to live in a 3-dimensional world. This gives us a way to think about the extra dimensions in superstring theory, though we may never fully grasp what they entail.